Hello, my name is Michael Birnbaum. Thank you for inviting me to give this keynote presentation. I wasn't a student of Norman Anderson. I agreed with much in the program of functional measurement and information integration theory. In particular, I like the idea of looking for models that had generality beyond describing a single judgment task. Except I disagreed with a few things, philosophy and methodology. And the distinction is between Anderson's idea of validation as opposed to the idea of testing and falsification. And I had suggested some methodological improvements to the system, scale convergence, the scale-free tests, and the use of joint independence, and I'll describe those today. I also found different empirical results. And today I'm going to be focusing on impression formation and the size weight illusion, which are two empirical situations that Anderson featured in a lot of his work, including the 81 book that I notice many people cite as describing his approach. Instead of what Anderson found, parallel lines, I found divergent interactions. And I also disagreed on the theory, whereas Anderson liked to use constant weight averaging models. I found results that were different and results that led me to argue for configural weight averaging. In particular, the kind of configural weighting that I found was rank affected configural weighting. It turns out that later people introduced what are called rank dependent utility models. And those models are also examples of configural weight models, but they differ from what I had in mind initially with configural weighting. And those two classes of models, the rank dependent and rank affected configural weight models, are different ones. So let's go to the beginning and make sure we're on the same page here. We can write out the assumptions of an additive model for two factors. First premise is that the scale values for the rows, I'll use the notation S sub R sub I, are independent of the scale values for the columns, call those T sub C sub J, and scale values for the columns are independent of the rows. In other words, in impression formation, the subjective value of an adjective is independent of whatever adjective it's paired with. Second premise is that the combined integration, the people combine this information, follows an additive model or an equivalent, in this case, constant weight averaging model. And the third premise is that the response, R sub ij, is a linear function of the subjective value. So I've written it here as A times psi sub ij plus B plus epsilon, where epsilon represents a random error component. Now, the additive model assumptions imply that if the errors have zero means, then the curves are expected to be parallel. And if the errors satisfy the usual ANOVA assumptions of normality and so on about their intercorrelations and so on, then we expect no significant ANOVA interaction row by column in a factorial design where the rows and columns might represent two sets of adjectives. Also, if the model is true, then the marginal means provide estimates of the scale values, which if the errors are in fact zero, these are unique to an interval scale in the sense that any linear transformation of both sets of scale values, when added, will be linearly related to the data. And a test of interaction is a joint test of all these assumptions taken in conjunction. Here's an example, Anderson 1962 data as reproduced in Anderson 1981. Here's a factorial design, or at least a two-way factorial design, where level-headed, unsophisticated, and ungrateful have been paired with good-natured, bold, and humorless. And the dependent variable is a mean liking of a person who might be described by those pairs of adjectives. And the curves in Anderson's experiment here are fairly close to parallel. And there's a subject, another subject there, subject RH is plotted over on the right, not quite as parallel, but Anderson then explained how the parallelism shows all these things about the data, and that's described in that 1981 book. Here's another example from the same book showing data from a 1970 experiment on the size-weight illusion. The first experiment on the left, there's a kind of a bulge interaction that is altered by the use of a different response scale. There's a rating scale in one case and line mark scale in the other. And Anderson concluded those were fairly close to parallel, and so he's fitting an additive model to the size-weight illusion. Here's a diagram or a schema for talking about the premises that we had used in that three-premise argument. The stimuli have physical values phi sub k. There's a psychophysical function that's labeled h in this diagram. These are integrated by an integration function I, forming the subjective integrated impressions, which are transformed by a judgment function into the overt response r sub I through n for the n stimuli. Now, Anderson argued for validation. He argued beyond that the ANOVA was testing all the assumptions that went into it to validating. He argued that the parallelism, the lack of an interaction, validates the model, the response scale, and the interval scale values all at once. The problem, of course, is that many theories can imply parallelism. For example, you could have a multiplicative model for the integration function with a logarithmic judgment function, and that would, because the log of a product is the sum of the logs, that would also produce additivity. And many other combinations of I and j would work, and it's also possible that scale values could change in context, and the changes could go unnoticed in still producing parallel lines. So let me describe the background and how I got involved in this research. I was a student with Alan Parducci as an undergrad and a grad student. Parducci's research shows how the judgment of a stimulus depends on the other stimuli with which it's presented. And Anderson was skeptical of Anderson's assumption that I had labeled here, P1, the independence of the scale values. The idea that the adjectives weren't changing their meaning in context, or that the value of psychophysical stimulus wasn't changing depending on the stimulus you're presented with it. And Parducci thought that maybe there are shifts in scale values that might be going unnoticed. And Parducci, Thaler, and Anderson joined in after Parducci and Thaler were collecting data in that paper. And they found some interactions and other results that showed an indication of some of the phenomena that Parducci was expecting. Here's some pictures of Alan Parducci, and he worked on contextual effects in judgment in many different domains. So he was also interested in general judgment decision-making and did work ranging from psychophysics to the theories of happiness, and it was his philosophical and practical interest in the problem of human happiness that really led him to do his psychophysics research on his approach, which was range frequency theory, a theory of how the stimuli influence each other. I joined the Parducci lab in 1965, and here's some pictures of me, probably 1965 to 66, working with the equipment. In those days, we had key punches and big equipment to run the psychophysics studies. All this could be replaced, of course, by much smaller pieces of apparatus today. Now, by 1967, there was accumulating a lot of evidence of interactions. Parducci et al. Had done the experiment on the loudness of combinations of tones that I cited a little earlier. And working with Parducci and Gifford, I had evidence on the judgments of the average length of lines, working with Clarice Veet on the average heaviness of lifted weights. People would lift 2 weights and judge their average heaviness. I'd also done work on moral judgments, how moral or immoral is a person based on the list of the deeds that they've done. And I'd collected data on impression formation and with Clarice Veet on the size weight illusion. And there was already accumulating a lot of evidence of interactions. In today's talk, I'm going to focus a bit more on impression formation and size weight illusion, 2 that I showed you from Norman Anderson's 81 book. So here are some results for impression formation. I did 3 experiments, each with a different sets of adjectives and a different set of 100 subjects, and plotted on the y-axis are the mean judgment of likableness of a person described by adjectives. I apologize for the poor quality of the image. This is a screen capture of a PDF of a photocopy of the article out of the journal. The lowest point on the left panel, it represents the mean judgment of a person who's mean and phony, and the adjectives are written on here. Mean for the row, the lowest line there is all pairs of adjectives that include mean. Phony is written across the top. Phony, squeamish, blunt, informal, or sincere. And so that lowest line are the mean judgments of how much would you like a person who's mean and phony, mean and squeamish, mean and blunt, mean and informal, or mean and sincere. And the highest point on the curve there, the highest point in that panel is rated liking of somebody who's sincere and trustworthy, which is much higher, up around 8 on this scale. And that top curve is for people who are phony and trustworthy, squeamish and trustworthy, blunt and trustworthy, informal, or sincere and trustworthy. And you see that the slope of the curve, or the amount of change in the y-axis, depends on the likableness of the common adjective, whereas in a constant weight averaging model, these curves should be parallel. Instead, they diverge to the right. Another group of 100 subjects with another set of adjectives. We also get divergence with some other kinks and twists in the figure, but the big picture, we see a big divergence to the right. And the rightmost panel is another set of 100 subjects. You see there's ample evidence of divergent interactions. Now, in those days, at Alan Parducci's advice, I wrote letters to Anderson and showed him some of the results I was getting from the 66 and 67. And we started a correspondence that went for a number of years from 67 to 72. And these were friendly letters. And yes, when I say they're letters, I mean things that you wrote on paper, or in Anderson's case, that he had a secretary type up and that were sent by the United States Postal Service, which in those days was much less expensive and also delivered letters faster than they can today. And there was a lot of discussion of many points, of disputes and arguments, and he was very much interested in the results that I was getting. But the main gist, I would say, of the messages I was getting from Anderson was that the interactions must be due to an invalid response scale. And I had a similar argument with Amos Tversky in 1970 at the Math Psych meetings in Miami. And Tversky argued that, well, if you can rescale data to additivity, then you should do so. You don't really have evidence for anything beyond an additive model. Here's a diagram of what that amounts to, rescaling to parallelism. On the left, that's the average of all those 3 panels averaged together. So That's sort of the average result of those levels of liking. And you see the big divergence, although parts of it you see, if you were just to pick out maybe the top 3x3 or a middle 3x3, the data don't look as bad from parallelism. And that little dashed box shows you the domain of one of Anderson's experiments relative to the domain that I did. So one of the arguments is the reason that he was finding what looked like parallelism is he was working with a much smaller range of values in his typical experiment. That's the one from Lampell and Anderson there. The panel on the right shows the results of what happens when you transform the data to parallelism. So the panel on the right shows that we've taken the data on the left and preserved the rank order in order to transform it to parallelism. This isn't always possible. For example, if the data if they cross over, or if they violate double cancellation or certain higher order cancellation, it may not be able to transform the data to parallelism without those lines showing the transformation. So you can read a point, read it across to the y-axis on the right, follow the line, and then project it over to the right, and that's the image of the point. After it's been inverted, our interpretation is that the inverse transformation, j minus 1, representing the inverse of the j function, is what that transformation accomplishes. So the question is, which of these two theories of impression formation is correct? We have the constant weight interpretation, which is that the data should have, basically we could still preserve independence. We have the constant weight averaging model where there's an initial impression, in this case, W0 times S0. There's a weight for the rows, W sub R, and it multiplies the scale value for the row, which is S sub R sub I, plus the weight of a column stimulus times the scale value for the column divided by the sum of the weights. And there's a non-linear but monotonic judgment function J that maps the subjective values psi ij into a response, and there's still maybe some random error on there. And so that's the interpretation. When we go to rescale to additivity, or in this case to the constant weight averaging model, we're saying, well, we're only assuming that the response scale is a monotonic function of subjective value. And the other interpretation is there's something else going on, that the interaction is actually real. And the interpretation that I was working with and continue to work with is a configural weight interpretation. And this looks just like the constant weight averaging model, except you'll notice a term there in the numerator, omega times the difference in the scale values. And what this omega times the absolute difference does, for a time this was called a range model, but it's a configural weight averaging model, is it transfers weight from the lowest to the highest ranked value. And if omega is negative, then it transfers it in the opposite direction. I'll show you some diagrams. This can range from a minimum model to a maximum model. And in between, if omega is 0, it's a constant weight averaging model, but it's a little more general in that it can produce divergent and convergent interactions. And that the judgment function was close enough to linear that basically what we saw in the graph is it's actually something going on psychologically and not something that should be transformed away. And of course, there's two ways to transform it away. One way is to try to change your procedure for collecting the response, and the other is to go ahead and just use a program like Mononova to transform it. And indeed, one of the ideas that Anderson suggested is, well, try changing your response scale. So I reasoned, well, if you are objecting to the response scale, your theory is that maybe the numbers 1 and 2 are psychologically farther apart than the numbers 7 and 8. So we need to do some transformation. Why don't we just reverse the scale? Instead of rating 1 to 9, how about we rate 9 to 1? We rate dislikableness instead of likableness. And no, we got the same interaction once you turn the scale around. How about if you use a 20-point anchored scale, as Anderson had done quite a bit of his work? Well, I got the same interaction. How about if you use a a line mark response with anchors and things, I got the same interaction. And how about if I said, well, how about we get rid of a numerical response and I just take pairs of adjectives from Anderson's list. He had a list of 555 common and meaningful adjectives that could describe personality, and he had ratings of them. How about we take pairs that are close together on the list, that are right next to each other on the list, and have somebody say, how much would you like somebody who's, say, phony and mean, or how about phony and intelligent? How about you find a pair from Anderson's list that are close together and match them? So we're matching two adjectives to two other adjectives, but two of them are homogeneous in value. And we take Anderson's rating, and I got the same interactions. So by the principle of converging interaction, I concluded the interaction is real. Here's the results of that experiment. You see there's, with a reverse scale, that's the upper left panel, with a 20 category anchored scale, you get the same interaction. With a line mark response, you got an even bigger interaction. With the matched pairs, you got the same interaction. Well, you could go beyond that. That wasn't going to convince somebody like Amos Tversky, who said, well, if you can transform it to parallelism, then you should. And so I proposed two criteria, stimulus and response scale convergence. And these are criteria to justify a transformation, a rescaling to parallelism. One says the J function should be lawful. In other words, it should obey some psychology there. We shouldn't say we don't care what it is, we just transform to get our additive model. The J function should be describable by a psychological law, psychological principles. And one of the principles or sets of principles in later work we use is Parducci's range frequency theory, which is a theory of the J function. It may be a theory of more than that too. But one interpretation is that it is a particular theory to describe, to allow you to predict what this J function should be. And at least in the scale convergence criterion, I stated it this way. The J function should be the same if the same stimuli, the same stimulus distribution, and the response procedure stays the same. And if that's the case, then if I use the same pairs of adjectives, the same factorial design of adjectives, and I have people judge differences between the adjectives. So how much more would you like somebody who's sincere than somebody who's phony? Or how much more should you like somebody who's sincere than somebody who's mean, or somebody who's unaccommodating or blunt or whatever? It should show the same interaction that I get if I have people judge combinations. How much would you like somebody who's sincere and malicious? I also proposed the idea of stimulus scale convergence, which is the idea the H functions, the scale values, should be the same for multiple operations on the same scale. That is, for differences governed by subtractions, and for combinations governed by an additive or constant weight averaging model. If you get the same scale values after you transform to both tasks to additivity, then you can say, okay, I can use the additive model to represent differences and to represent combinations with the same scale values. And so that's an argument that instead of having two homomorphisms between empirical and theoretical structures, you have really one combined with the same scale values in both. So I collected difference judgments and combinations using the same rating scale. And you'll see that the difference judgments are pretty close to parallel. There's a point there that's a little bit out of whack with parallelism, but the interaction is not particularly large in statistical terms. On the other hand, for combinations, it is. So we're getting a divergent interaction for the combinations. When the two adjectives describe the same person, we're getting an interaction. When they describe two different people and people are judging the differences, we don't get the interaction. So by either stimulus or response scale convergence, we have to argue that the interaction is real down there. So both stimulus and response scale convergence are violated if you assume the additive or constant weight averaging model, because when you transform the data to parallelism, you get a scale values that are not linearly related to the ones you get for difference judgments. On the other hand, if you fit a configural weighting model, the scales converge, they agree. In other words, one set of scale values can produce both differences and combinations. And furthermore, you get pretty close to a linear response scale for the rating scale. Well, if that isn't good enough for you, then I propose the scale-free tests, which I started working with about 1970, and which were in my dissertation 72. It got eventually published in the JEP monograph in 1974. If difference judgments are functionally related to differences, they don't even need to be a monotonic function. They just need to be any function. Then you can use differences between combinations to directly test the additive model. So let's judge differences between combinations. How much more would you like somebody who's kind and sincere than somebody who's mean and sincere? And maybe you should take a moment just to think about it. Think about a person who's kind and sincere. How much would you like them? And think about somebody who's mean and sincere. How much would you like them? And then think about the difference in between the liking between those two people. Now think about somebody who's kind and phony versus somebody who's mean and phony. Most people say that second difference in liking is much less than that first difference. And that's directly showing you there's an interaction. On the other hand, if you have an additive model here, we've got sincere on both sides. If it's kind plus sincere and mean plus sincere, you could just subtract off sincere from both sides if there's no interaction. And this is kind and phony versus mean and phony. So phony is the same on both sides. You can just subtract it off from both sides. So in both cases, this should just be the difference between kind and mean. So if there's no interaction, these two difference judgments should be the same. But instead, the data violate that. You can also use a subtractive model to rescale the data to parallelism to fit the subtractive model and estimate the combination values. And that's what's plotted here. And so we see that these scale-free values, in other words, we've already used monotonic transformation to fit an additive model of difference judgments, and they show the same divergent interaction, but the direct judgments of differences show the same effect. We applied the scale-free test to the size-weight illusion. So Clarice Veed and I did that experiment with the size-weight blocks. And we had previously done work on heaviness averaging using scale convergence, incidentally, and showed that the constant weight averaging model should be rejected for the average heaviness judgments. We also used scale convergence to argue that even though the ratio model fit judgments of ratios, we should reject it if we assume that difference judgments are governed by subtraction. So we found that models that were violated the parallelism prediction could be rejected. And we found cases where models fit, and yet we still wanted to reject models, even though they were fitting the bilinearity prediction of the ratio model, which is kind of multiplicative model. If you think about it, it's just the numerator times the reciprocal of the denominator. Well, we also did the scale-free test we applied to the additive model of size-weight illusion. And when I wrote to Anderson about these various lines of reasoning, he said, oh, you're going down these dark and treacherous paths, and I should come to UCSD, and he could show that, if we use the appropriate procedures, these kind of nasty interactions and this complicated reasoning wouldn't be required. So I proposed to go as a postdoc in 72, 73. I finished my degree in 72, and I went to San Diego hoping to convince Anderson to expand functional measurement, because I thought all this time I was contributing to a field of functional measurement and information integration theory, and that it should include functional measurement and information integration theory should include scale convergence and the scale-free tests, and it should acknowledge that the additive and constant weight models are not descriptive and something else is required. And I was arguing, of course, for configural weighting for impression formation. So we needed to revise the models of information integration theory. I think Anderson was hoping that my interactions wouldn't be found at UCSD. He had talked about these motley groups of UCLA students and didn't trust them, although he had been a faculty member at UCLA, so maybe he did know something about UCLA students. I don't really know, but he thought, well, if you use the bright end anchors and you use a properly dressed lab assistant and pay the subjects and test them individually, they'll take the tasks more seriously. And under those conditions, these models that he was working with would be found to be empirically descriptive. I had talked to Dave Weiss about some of these things. Dave Weiss was a student of Anderson. He was had left San Diego, I guess over some disagreements with Anderson. I'm not sure exactly, but he had taken a job before finishing his dissertation, which I think he was still working on at that time. But he said, "You're not going to enjoy your postdoc." At any rate, when I got there to work with Anderson, and he had some odd characteristics. I mean, the man could be extremely charming and outgoing. He was a good speaker at his talks, which are very much like his writing style. He would present the material in a very logical and efficient manner. And so his presentations were quite clear. And in person, when I had met him at meetings, he was quite charming, but he had some other peculiarities. And one of those I discovered when I went to meet with him at the postdoc. I went in his office and he said, "So what are you going to work on during your time here?" And one of the things, of course, to work on was to show him that the scale-free test of the size-weight illusion led to violation of the constant weight averaging model or the additive model for the size-weight illusion that he had been working with. And I expected to get the similar results to what Clarice Viet and I had gotten with our first study. And I described that experiment. He sat there in silence listening to that. And I finished that presentation. I erased the board, put another experiment up on the board that I was planning to do, and I explained, so if it comes out like this, it means this, and if it comes out like that, it means that. And he sat there looking at it. And so then I erased that, and I presented another one and another one. And after I'd presented about 5 or so ideas for things to do while I was there, at the very end, he said, he went up to the first one and he pointed to the ghost of the chalk that had been erased. And he said, "So if it comes out like this, it means this. And if it comes out like that, it means that." And I found out later from talking to the grad students there and also Jim Chanteau, who was a former student, that this wasn't uncommon for Norman Anderson to go into these silences. Lola Lopez told me that she just couldn't stand the silence and would continue to talk the whole time, apparently as I had done. And Jim Chanteau said that, he figured this out and he would bring work with him to do and a pad of paper, and he would present something, and if Norman Anderson went quiet, he would write down what the point was where he went quiet. Then he would take out his other work to do and he would start working on that, and he would sit there and work in the office. And then at some point, maybe 40 minutes later, Anderson would begin to speak again, and he would look at his pad to pick up where he was. and they would continue the discussion. But at any rate, I had proposed to Anderson to do all the features that I had cataloged from our correspondence and that he might want to suggest, so that I could do this experiment with the size weight illusion using the scale free test. And the design was to include the end anchors, the kind of response scale that he would like, that we would pay the individuals and test them separately, and also use the lab assistant that he had designated who wore the appropriate clothing and demeanor. I'd found out from the students there that they had gotten, I said, well, don't you students find these kind of interactions that I do? And sometimes they would say, well, yes, this student used to get those divergent interactions too, but Anderson said that she didn't wear a bra, and that basically, if you were going to run experiments, you should wear a lab coat, and then the students would take it seriously. And so he had various ideas about the conditions for running the experiment in order to get these results. But at any rate, I had gotten a little bit of funding with my postdoc. We paid the individuals who were going to be tested to use hired the approved lab assistant, and the data came in extremely clean and beautiful. And they showed an interaction that was neither additive nor exactly multiplicative. And I drew up the data for the graph for each subject, and almost every subject had almost the same, that's what it's going to look like, almost the same interaction. And I showed Anderson graph after graph for each person. And the only thing I can remember that he said is he pulled open the drawer, his pencil drawer on his desk. And he said, I wish I could take out some error from this drawer and sprinkle them on these data. And then there was silence. Now here's what the data looked like. This is what the data looked like in the mean judgments, the marginal mean judgments, but also what they looked like individually. These are after they've been rescaled. What's drawn here is also after rescaling. Rescaling basically was close to a linear transformation with some small kinks here and there. So these were the data collected by the hired assistant, and to my disappointment, Anderson did not cite this experiment in '81 in his book, where he presented the size weight illusion as being fit by an additive model. Here's a summary of the situation for scale-free tests of the impression formation and of the size weight illusion. For impression formation, too high versus a high and a low adjective, you get a rating of about 2.61. And the difference between a mixed high and a low adjective with two lows is a judge difference of 1.29. So it's about twice. People rate that difference between sincere and kind and sincere and mean to be about 2.61, whereas between say malicious and sincere and malicious and mean, the difference is 1.29. For the size weight illusion, the difference between two sizes of the same weight was 1.48 at 400 grams and only 0.62 at 50 grams. So that's more than twice the judge difference. And the difference between 400 grams and 50 grams at a small size is 8.31, and at a larger size is 7.26. So there's the direct judgments show evidence of the interaction. Well, in 1982, I wrote this chapter that I recommend to you that summarizes the places where I disagreed with Anderson. Section F of that controversy, there are other controversial issues in measurement that were reviewed in that chapter as well, but Section F gives a discussion of functional measurement as I saw it, which included scale convergence and scale-free tests, and constant weight averaging models versus configurable weight averaging models. I also took Anderson to task for what he was calling cross-task validation and the two-stage integration as examples of validation of the response scale, and showed that these don't really qualify under the criteria that I had set forth. And you can read sort of more details than I just presented about these controversies in that chapter. Now, this would be a place where I could stop the talk if I run out of time, but there are 40 more years of results to present, which have amplified, extended, and strengthened the case that I made in the 82 chapter, but also have led off in some other directions. So I want to present those briefly if there's time permitting here. You can do a scale-free test, not only with judged differences, but also infer subjective differences from reaction times. And so in 1990, Jerwan Zhou and I published a paper that had begun 5 or 6 years earlier. Well, actually, now that I think about it, about 8 years earlier, where we developed a model of response times and difference judgments. And there are 3 phenomena in response times. There's a distance effect, and that's primarily what we're going to use it's the distance effect that's basically got us initially interested in it, because things that are subjectively far apart are fast for people to discriminate. And things that are closer together, it's harder for people to decide which one is more, which one's better, which one's more likable. But there are also phenomena that mean that you can't just use the response time as a direct measure of distance. There's an end effect and a semantic congruity effect. And we developed a model of these 3 phenomena of response times. And this same model also used the same scale values. So it had preserved scale convergence with difference judgment. So we have a model that represents 3 matrices of data: a matrix of judged differences, and a matrix of more response times, which person would you like more, and of less response times, which person would you like less. And then we applied that model to people described by combinations of adjectives. Well, here's basically the idea of the experiment. First, there's a learning task. So people learn to associate names to adjectives. They learn things like Bill is sincere, Fred is mean, and Carl is something else. And we counterbalance so that the names got paired with different, so the name Bill wasn't always paired with sincere, but Bill might be paired with mean and Fred with sincere. So we're going to be talking about the adjectives rather than the names. They were all 4-letter male, common male names, used frequently and every day. So then there was a test of paired associates learning, so that we were convinced that the people had learned that, yes, they had imagined Bill, and Bill was sincere, and they had imagined Fred was mean. And if you asked them how would you describe Fred, they would say Fred's been described as mean and Bill has been described as sincere. So we're sure 3 times in a row that they knew the adjectives that went with the names. And then we had 3 tasks for them: choice reaction time, the time to say which is more likable, which is less likable, and the rated differences. So here's what you'd see on the screen is what's below here. People would look at the plus, the screen would otherwise be blank, and then the words Bill and Fred would appear until the person pushed a button on the right to say which was more likable, or to say if Fred was more likable, and the button on the left if Bill was more likable. And so that's the more reaction time. Which would you like more? Push the button corresponding to the name. But they also had a task on another block of trials where they had to say which was less likable. And so if Fred was less likable, they'd push the button on the right, and so on. So this counterbalanced across position and the names to get the adjectives. And here are three phenomena. The distance effect, the farther apart, if you have 7 adjectives, they could differ by 6 steps, by 5 steps, by 4 steps, or by 1 step, according to the differences in level. And the dashed line is the prediction of the model, and the points are actually the response times that we had measured. There's a little discrepancy here, but this is based on less data as well. So the model does a pretty good job describing the distance effect. It also describes the end effect. So anything involving the most likable or least likable adjective or person is going to be a faster response time than anything involving 2 persons in the middle of the scale. And again, the dashed line are the predictions, and the points, the markers here represent the data. Does a pretty good job of that. And it also describes the semantic congruity effect, which is that if 2 things are both likable, it's faster to say which is more likable than it is. Of course, things in the middle are always slower than it is at the lower end. And if you ask which is less likable, 2 things at the low end, it's faster to say which is less likable between 2 things at the low end, things differing by 1 step. That's the semantic congruity effect. And again, the points are the data and the lines are the predictions. We then applied this to combinations. So now the learning task involved Doug is malicious and intelligent. And there were again, and Fred and all the same kind of names. And there were again 3 tasks. Which do you like more? Push the button for the one you like more, push the button for the one you like less, and judge the difference in likableness. And again, we have a model, that same model we fit to all 3 matrices of data with the same scale values for the people who are now combinations. And the estimated combination values show the same interactions. Oh, I see, I didn't produce the graph, but they again show the same divergent interaction. Just to illustrate how the data look, the mean judge difference between loyal and understanding and loyal and obnoxious is 4.48. Between malicious and understanding and malicious and obnoxious, the difference is only 3. And so that's again confirming a divergent interaction. But the response times for the things that are farther apart are now faster response times. So the time to say less is 2.46, but it's 3.23. The time to say more is 1.82, but it's almost, it is a whole second more to say, to respond which you like more between malicious and understanding and malicious and obnoxious. Now, models of evaluative judgment, like how much would you like somebody, are analogous to models of how much you'd like gambles. So people are sort of gambles because you don't know what they're going to do at any given time. And gambles are like lotteries that have certain probabilities to win different amounts. And these amounts are like the adjectives, or analogous to the adjectives. There's 2 theories of risk aversion. Expected utility theory, which is like the constant weight averaging model that Anderson promoted, says that what you need to do is, if you have a 50-50 gamble between $0 and $100, it's not worth $50. That's expected value. It's worth less. Why? Well, because the money scale is not linear. If you transform the money scale, you realize that the difference between $0 and $20 is greater than the difference between $80 and $100. And so on this transformed scale, $33 is the right balancing point. If you say to people, which would you rather have, $50 or 0 or 100, people say, I'd rather have $50. And the balance point is, for my undergraduates that I test, is around $33. People will say, I would be indifferent between $33 for sure, or this gamble that I could win $100 or 0 with equal likelihood. Well, the configural weight interpretation is, in addition or aside from there being a transformation needed here, the big story is that what's going on is there's a transfer of weight, and there's people, just as people put more weight on the dislikable adjective, they put more weight on the bad thing that can happen. The 0 might happen, and because it gets like twice the weight that $100 gets, the thing balanced, just as malicious or mean, phony, those adjectives get twice the weight of a good adjective. The balance point here, just as a combination of a good and bad thing was kind of dislikable, a gamble, which could give you 0 or 100, is not as good as the expected value, but $33. Here's an analysis of the configural weight model that I described with one extra parameter. What's labeled W is the omega parameter I was talking about before. And it can go from a minimum model to a maximum model with a parallel averaging model in between, with various kind of divergent and convergent fans in between. This is what the indifference curves look like. These are, if you took expected value theory or expected utility theory and you transformed the data, you transform these data up here to parallelism, these are the inferred scale values you get. So it shows the, if a person believed in utility theory and actually the theory was configural weight model, you're going to get a negatively accelerated function. So you can apply the scale free test to decision making as well. And Birnbaum, Thompson, and Bean, in fact, did that. Scale free test of binary gambles. You set up a factorial design of X and Y, and you have people judge the differences between them. And so we ask questions like this. How much would you pay to get a $100 versus 92 50-50 gamble? In other words, once you own the right to play this, you're either going to get 92 or $100 instead of the gamble. In other words, suppose you have now the gamble 50-50 are going to get 100 or 8. So you're exchanging one gamble for another, kind of like you're trading in one car, paying them some money and getting a different car. So to get this gamble instead of this gamble, how much would you pay? And people judge that to be worth $55 more. So it's worth paying $55 to get this gamble instead of this gamble. Well, how about to get this gamble, 692 instead of 68? People are willing to pay 27. But notice if you have an additive model, the 100 is the same, and this is just the difference between 92 and 8. And here 6 is the same, and this is again just the difference between 92 and 8. So if you have an additive model, those differences should be the same. And yet people are willing to pay about twice as much to get a 92 instead of 8 when the common value is 100 than when it's 6. Now, here's another line of work that I did. If the interaction is real and if we understand it, we should be able to alter it. So working with Steve Stegner, we manipulated the point of view, asked people to judge buying and selling prices, again, of used cars. This manipulation later got to be called the endowment effect. 1980, Thaler came in and started calling it the endowment effect and tried to explain it with prospect theory. I published a couple of years ago an article reviewing the attempts to explain the endowment effect with prospect theory. It's also in the appendix of a paper by Birnbaum and Zimmerman. I can give you the reference if you're interested in that. But my point here today is we want to manipulate the interaction. Birnbaum and Sutton did something similar, as did Birnbaum, Coffey, Millers, and Weiss. So let me show you the kind of, this is what 1979, experiment 5. We've got how much would you pay to buy a car given estimates that say that it's worth $300 and another estimate says it's worth $650. Of course, all prices have gone up. You could multiply them by maybe by 10 to get into present currency. And we have divergence for the buyer's price and also for fair price. That's what should you, if person A destroyed person B's car, and you're a neutral judge, and you're trying to decide how much should the person who did the destruction pay the other person so that it's fair to both sides, you also get a slight divergent interaction. But seller's price converges. And that experiment was repeated in different ways, and we get the same thing. Here's Birnbaum and Sutton judging how much is a gamble worth, where you have 50-50 chance to get either $0 or $96. If you're asking people what they'd pay for it, it's very small, at least this subject. This is subject number 1, who showed the effect quite extremely. And so I'm showing you this extreme subject. The average data are reported in this paper and also show this same kind of shift, but less extreme. But this also shows you how clean individual data can be. These are single judgments plotted up here. So this person was willing to pay very little for a 50-50 gamble. On the other hand, if you said you already own it, what's the least you'd accept to sell it? That point, here it is. This is 0 to and versus 96, 50-50, 0, 96. They want more than $60 for it if it's a selling price, but they're willing to pay less than $10 if it's a buying price for it. Now, between these two conditions, you can derive the psychophysical, the scales of money, and the scales agree if you fit a configural weight averaging model, but not if you rescale them to parallelism. So there's another scale convergence argument was used in that paper. Now, another argument is called joint independence, which says that if you have 3 factors, so far what I've been talking about is with what you can do with 2 factors. With a 3rd factor, it should be the case that the rank order, if you have 3 factors, call them capital X, Y, and Z, the rank order within the XY submatrix should be the same for each level of Z. If you think of this as a rectangular solid with pages, or with pages, different page two-way factorial design. In other words, if X, Y, Z is preferred to X prime, Y prime, Z, notice Z is the same here. And so we're looking at the ranking of X, Y versus X prime, Y prime. That should hold if and only if X, Y is preferred to X prime, Y prime when Z is changed to Z prime. In other words, the rank order of judgments in the X by Y submatrix should be the same whether capital Z is equal to Z or Z prime. But you can get violations of joint independence. And with Jacqueline Zimmerman and I studied investments based on predictions of the future value of these investments from advisors. And we got divergent fans of curves. We observed those for the buyer's point of view and convergent from the seller's point of view. So we can get the interactions. The interaction will be changed. The configural weights allow you to predict where to look for violations of joint independence. So you can basically fit the model, estimate the scale values, estimate the configural weight parameter, omega, in that first graph that I showed you. And for example, based on our first experiment, it was predicted that the selling price of $299.50 and $1,050 should be greater than the selling price of $200, $600, and $1,400. But the selling, notice that the 200 is the same on both sides. And if we now change the common thing to 1600, and so we still have 600 and 1400 on this side, we still have 950 and 1050 on the left side, we should get a reversal. And that reversal in rank order is predicted by the interactions observed in the first panel. So anybody that says scale them away is saying you're not going to get any violations of joint independence. So the two matrices really should be the same. So this is predicted for the seller's price, but not for the buyer's price. Buyers should prefer the safer investment in this case, in both cases, because they're so risk averse, in fact. This is based on risk neutral, because notice the mean value is the same on both sides. You have to change the mean value if you're going to get a violation for buyer's prices. We made 40 predictions, and 40 out of 40 were correctly predicted from one experiment. From the model fit to the means of the first experiment, we predicted the change of rank order of the means in the second experiment, 40 out of 40 predictions. A similar thing was done with gambles as opposed to with investments by Birnbaum and Beagley. We did even better version, in my opinion, of predicting it. We have two things, of course, to predict. One is the interaction and also the change of interaction. So the violations of joint independence by themselves can't be transformed away. And secondly, we're using the change of interactions to predict a change in where to find the violations of joint independence, and we're able to do that. Joint independence is an example of a critical property. And so in the last 2 decades, I've been developing and testing properties or using properties that other people have proposed, like transitivity, to rule out classes of theories. And so the problem is still the same: to understand what is a descriptive model of information integration, evaluation of gambles, of investments, and of person impression, and so on. But instead of looking at parallelism, I've been working with things like joint independence. And so some of these properties, first order stochastic dominance, monotonicity with respect to the value, upper and lower cumulative independence, those are two that I invented. Interactive independence, that's another one. Non-comonotonic restricted branch independence, that it could be attributed to Peter Walker. Transitivity, integrative independence, and priority dominance. So the problem is to come up with critical properties that involve just 2 or 3 or 4 choice problems, and show that, or things to judge that show that the rank order can rule out classes of theories. And indeed, while testing these, the data are able to rule out original and cumulative prospect theory, Rankin-Stein-dependent utility theory, the priority heuristic, the simplified additive difference model, regret theory, and a number of other theories have been tested and disproved. So in conclusion, I'd say sometimes a rival, and I would regard Norman Anderson as having been a rival. I came in not as a student of his, but as somebody that had already been doing work in this field, inspired by Parducci's skepticism, that the assumptions used in this approach weren't plausible, given the idea that context and configuration could matter. But sometimes a rival can be a good friend by forcing you to accumulate evidence. I was forced by people like Norman Anderson, and by arguments with Tversky and later Kahneman, to force you to accumulate evidence and develop your arguments in order to clarify not only the results of the experiments, but exactly why you reach the conclusions you reach. And based on converging operations, scale convergence, and scale-free tests, and violations of joint independence, I've concluded that the constant weight averaging model can be rejected as a descriptive model in favor of something that includes an interaction like configural weighting. And further, that configural weighting depends on the judge's viewpoint. When you're judging how much you'd like another person, how much you'd pay to buy something, how much you would judge somebody else's morality, you're in the buyer's point of view, and you're going to get, if you're the consumer, you're going to get divergent interactions for goods to be consumed. I recently published an article in JDM on consumers evaluating vaccines for the COVID inoculation that we did just before the vaccines became available. By viewpoint, though, I mean, you could also be in the seller's viewpoint. You could be the one selling the vaccine, selling the car, selling the gamble, or trying to sell yourself, maybe from the point of view of a person who wants to get into heaven. You think the bad deeds should be forgotten, but from the point of view of a person deciding who's admitted to heaven, you get these biblical phrases such as, if I place a stumbling block before you and you stumble, then you'll die for your sins, and your good deeds will be forgotten. And that's the way moral judgments seem to come out when you're in the point of view of the buyer, when you're evaluating somebody else's morality as opposed to your own. Well, because the parallelism test is not sufficient to diagnose the model, I'm advocating that people should test critical properties that can provide clearer diagnosis of models of information integration than just doing a parallelism test. So with that, I'll thank you for your attention.